alloy strengthening for use in engines and other automotive parts. Please join me in welcoming Dr. Ghaffari.
I'm very glad to be here. Please let me know if my voice doesn't carry, but I tend to be loud, so I'm there. From atomic physics to automotive research, and yes, please.
No.
Okay, we're good. Is that better? Okay, great. I lost my train of thought, which is fine. Okay, so I'm going to tell you about how my path in physics seems to have been very different from the previous speaker. I think, I don't know if you guys managed to find two people that had different paths this much, but I think it's awesome because it will show you how there are many different ways that you can go and still find happiness, hopefully, at the end of the road. So background, I was born and went to high school in Iran. I was there during the Islamic Revolution, and so usually when I mention this, people are very surprised that I pursued physics. But my family happened to be very happy with people who got educated, and I was very nerdy. So to a certain extent, I think even if there were messages out there for me not to do this, because almost all of my family are physicians, and I was the only physicist, so to speak, among them, I didn't get the message. So it was all good. The problem with having been born in Iran, besides how difficult it was to get here and how many visa things I had to go through and how scary it was that because I was not a US citizen, I didn't have the summer research experiences that Christine had. And that, at the time, I didn't realize how much of a disadvantage it was. But for the freshmen and sophomore and juniors among you, please do that. I cannot tell you how important it is to kind of not only know whether you like physics and whether you want to be in the laboratory or whatever, but also how to interact with people, because you're going to be dealing with these people, hopefully, for the rest of your lives as you follow physics. I got a dual bachelor's degree from Eastern Michigan University, down the road, so to speak, in physics and mathematics, and then I came to the University of Michigan and got my PhD in atomic, molecular, and optical physics. So I didn't have any research experience, and I didn't feel like I was just needed to go and be independent. My research advisors were wonderful at answering questions and everything. But to a certain extent, I did feel like they gave me this big, huge lab with this big, huge instruments and threw me in there. And I'm amazed that I survived, to be honest with you, because there were some high voltage sparks that could have killed me, possibly. And I remember one time I almost put a hole through my vacuum system, and that did cost thousands of dollars, and I thought I had a heart attack. So it's, again, having that undergraduate experience where you kind of know what to plug in and what not to plug in and where you put your finger is really important. Get that experience as soon as you possibly can. So I'm going to tell you a little bit about my PhD in physics. All throughout my PhD, I was a foreign student. That did not affect my education whatsoever, but I needed to worry about whether I'm going to be able to stay in the US or not. So again, that issue of always needing to make sure that I can get a green card and stay was in the back of my mind. I did a postdoc at Rice University that I will tell you about also. And then I will tell you about the work I've been doing for the past 15 years or so at Ford Research and why I chose to go the route that I did. Okay, graduate school. So atomic physics at the University of Michigan, and my initial experiment was precision measurements of quantum electrodynamics in positronium atoms, which is a positron and electron, so it's a nucleon-less hydrogen with a positron instead of the proton. And when you read quantum mechanics books, I just looked up the name of one of my favorites, Iceberg and Resnick. they describe these experiments in quantum mechanics, and you get that chill in like, how they describe they do it. And this was a really good example of what was happening. At the time that I joined the group, our group in experiments they had done in a lifetime of positronium had the only discrepancy with quantum electrodynamics. And that was the big deal, because for the first time, the theory did not seem to quite match experiments. Since then, it's been worked out, so no worries, everything was fine. But they wanted to, instead of looking at the lifetime of positronium, they wanted to look at the energy levels and see whether there was also the same discrepancy that can be viewed. So the idea was that you wanted to look at the energy levels of the 2 triplet S to 2 triplet P levels in positronium. And remember that positronium doesn't last very long, right? So the longest lasting state is 140 nanosecond lifetime, so you learn the experiment quickly, and the state we were looking at was even shorter than that. So this is a beautiful quantum mechanical like experiment that kind of pulled me in. So you bring in your positrons, they're charged, and so they bounce back from the voltage that you put on this mesh, literally a mesh. Everything is in a vacuum. You embed the positrons into the positronium, into a foil. It happens to be a metal foil, a clean foil. And then amazingly, because positrons are the antimatter of electrons, instead of going into the metal and just staying, they want to come to the surface and pop out. And because of that, in the process of coming out into the vacuum, they grab an electron from the surface, maybe from the junk, from the oil, leftovers, and make positronium. So you make the positronium, most of them happen to be in the ground state, and because they are neutral, they go through this mesh. So then what you do is some of them, very few of them are going to be in the N=2 state. You drive the transition from 2 triplet S to 2 triplet P, and then you have a laser beam that ionizes the N=2 positronium atoms, and you get your positron back, and that's your signal. Okay, so now the lifetime of 2 triplet S is different from 2 triplet P. So imagine if my microwave is on, and I have my positronium formed, I go through, I make 2 triplet S, I ionize it, and I get a signal, and voila, that's my background. But then I turn the microwaves on, and I do make the transition from triplet S to triplet P. That happens to be a much quicker decay, a much quicker annihilation, and that means that I have fewer positronium that makes it through to my laser beam, gets ionized, and my signal decreases. So very simple, you just track how, as you tune the microwave, your signal level goes down, and you get your levels that you wanted. So this is the beautiful part of it, but then real life comes in. So real life comes in and says, okay, I have a laser beam that I'm trying to ionize this positronium, and it needs a lot of energy to be ionized. And the only laser that I have in my option is a pulsed laser. It's a UV laser, but it only can be on, I think it was something like 40 nanoseconds every 20 microseconds or something like that. So imagine that you cannot do your experiment for 20 microseconds, then you do it for 40 nanoseconds, then you have to be off again. So your duty cycle is really low, right? If you had to just let your positrons be going in there kind of continuously as you usually do, it would take forever to do the experiment. So even though this was the main experiment, one of the main parts was building a positron trap, what I like to call a positron gun. So the idea is you have a vacuum system, it's relatively large, you have a radioactive source. The radioactive source produces a lot of high energy positrons, but you can embed them in a metal foil. They go in there, again, they thermalize. Because they're antimatter, they like to come to the surface, and so they come out as low energy positrons. You apply voltage to these are literally cylinder shells. Like these are shells of aluminum that you put in there, and you have a high magnetic field that makes sure that they're confined radially. They enter this trap, they go all the way over here, there's a voltage on this grid, it's again a mesh. They come back, but in the time it takes for them to do one round trip, you raise the voltage at this end, and they can't go anywhere. So it's literally like you're putting the stuff in and then just ramping up the door from which the positrons enter. So you end up just trapping them in there, and then in sync with your laser, you let them out, okay? So suddenly, instead of having only 40 nanoseconds worth of positrons, you have bunched together 20 microseconds worth of positrons. So your signal goes up. So this was the main thing. Okay? Is this okay? Okay. So, there's a lot of okays I said, right? So this positron trap actually turned out to be a lot more exciting than I had anticipated in the fact that it behaved very strangely. It behaved very strangely in that when it was supposed to work well, it didn't. And then I was all alone in the lab doing my thing. So another difference with Christine is you worked on big projects with lots of people. This stuff was mine. I would go unlock the door. It was a huge experiment. But I would turn on the voltages and I would do all of the tweaking. And it was awesome. It was mine, right? I could do whatever I wanted with it. So being bored and a nerd, I just changed the voltages and I put them up and put them down. And when it wasn't supposed to work based on normal understanding of these positron traps, it worked beautifully. The question was, what the heck is going on? So believe it or not, I discovered something. And I'm very proud of it. That's what I'm proud of, not the prize. But what I'm really proud of is that I was lucky enough, and lucky has a lot to do with it, because I happened to be at the right place, at the right time, and be obsessive compulsive and nerdy enough that when this thing didn't work, I had to figure out how it did. So I actually discovered a form of cloud transport in traps like this. So I don't want to give you a lot of detail, but imagine you have an extremely simple system like this. It is completely classical. There's no way that you would think that quantum mechanical or chaotic systems would come into this. And I don't want to go into a lot of detail, but what happens is that this is the voltage on that cylinder that I told you about. So this is the voltage of the main cylinder that provides the potential well that your positron is zooming back and forth in. It shouldn't really have a lot to do with how well you trap. So again, imagine that you literally, instead of positron, you're pouring in water, right? You pour water, it kind of trickles that way, it comes back, and then in the process you kind of raise the potential at this end. If you are a little bit off in that, it shouldn't make a difference. But what it did was that the number of positrons that were accumulated showed this very distinct feature: maximum, a lower maximum, higher maximum, lower maximum, so on and so forth. So what I ended up doing was wrote my own code in simulating what happens in this positron trap, and in the process, I knew exactly why there was a minimum, a maximum, another maximum, and it has everything to do with these beautiful Poincare sections that I didn't know anything about chaos. I still don't know anything about chaos, but I learned enough to be able to, and I had a great advisor, I knew enough to be able to put it together. So believe it or not, the fact that you have these very regular trajectories. So just imagine them as trajectories of positrons moving in the trap. You don't have to know exactly what the axes are. You have these very regular trajectories in this case that are the standard classical physics that we think about. But what happens is that at some point you get into something extremely chaotic, okay? So imagine that I'm raising the potential at my door, okay? But what happens is that the positron barely comes back and says, wait, I gotta turn around because the potential is too low or is not low enough, so it goes back down. But again, imagine that you have an object who's doing that. The little bit of the changes of my knuckles and how they're formed and what the angle is gonna have an effect whether the positron goes this way or goes this way, right? It is that simple. So it is a question of, okay, it is not that simple, but, so it is all a question of the fact that when you have a minimum, you have these regular trajectories lasting a long way into where the phase space is, so you don't do a lot of trapping. But when you have the maximum in here, which is the Poincare section you see here, the chaos goes a lot closer to your knuckle, so you end up having much better trapping. So that was awesome. That was, and again, I say this not only because I'm proud of it, but because we sometimes think that, you read about Einstein and you read about Planck, and you think to myself, oh my God, there's nothing that I can discover out there. that is not the case, right? You have to get lucky and you have to go after it. There's a lot out there that people do not know how to do and they do not really consider it. So this was very nice. So what I'm trying to show you is the different flavors of physics, right, to a certain extent. So let me go back to this. So we had a large atomic physics group, and in this group, pretty much everyone did atomic physics. They didn't do beam physics, which is what the positron trap was all about. And we had this research scientist who had this big beard and gray hair, and he was scruffy. He looked like a Santa Claus after having drunk too much. So, and we didn't talk a lot because my experiments and his were not really, together that much. But he totally amazed me. And once I figured out how this trap worked and made it work, and he saw how many months it took, because my advisor wasn't really interested in the trap as much, right? He wanted me to get to the positronium experiment. He actually made a little plaque out of it that said Betatron. There are actually accelerators out there that are called Betatrons. So he made a plaque that said Betatron after my name and put it on the experiment. And that was awesome. I still have it. It's a great thing. And that was pretty much one of the only warm moments we had. He was scruffy, and when I said something that was wrong, he would beat me up. But underneath it all, it was really awesome. So that was an extremely good experience. But as I was getting my PhD, my field changed, right? So when I talk about precision quantum mechanics experiments, a lot of you might not even know what I'm talking about. When I entered physics too many years ago, that was one of the main atomic physics things that people did. Look at QED, see what happens, whether the experiments go in. But as I was getting my degree, and it took too many years to get my degree, Bose-Einstein condensation was becoming the big thing, right? And so the tendency is once an experiment succeeds, and kudos up the wazoo to the people who made it work, because they took years and years to make this thing work. Suddenly, Bose-Einstein condensation was everything. Pretty much all the funding that was in atomic physics was being channeled through to Bose-Einstein condensation, which makes perfect sense. The corollary is when my advisor entered physics, electron scattering was a really big thing. Everyone wanted to scatter electrons from everything on the face of the earth and know where the spectra is and find out. So the joke we had in the group was that we would go to these conferences, and there was a whole session of electron scattering from wifnium, wafnium, wafnium. So again, the field changes, right? The thing that makes the NSF funding person excited changes. So I was excited about Bose-Einstein condensation. I wanted to go into it. So that's what I did my postdoc. So I went to Rice University to the third group that was able to achieve Bose-Einstein condensation with lithium-6. But the race for the Nobel Prize was on. And as you know, the Nobel Prize is given to only 3 people. And there were 4 in the running. So there was a whole bunch of got to get there first going on. So the way you do that is you make the degenerate Fermi gas, right? So the Bose-Einstein condensation has been done. You make the Fermi degenerate gas, and then you're all set. So this is what the experiment for that looked like. So, and it's complicated. I don't want to go into too much into it, but you first need to make a Bose-Einstein condensate to cool down the Fermi degenerate gas. So what we did was we had a lithium-6 oven, hot lithium atoms would come off of it. This is a magnetic guidance system that gets rid of the fast ones, so only the slow ones make it into the vacuum system. I had a vacuum system that was 10 to the minus 10 torr. I mean, it was really good. These suckers need to be in almost pure vacuum because they need to sit there for many seconds and many minutes. So the amount of, the kind of vacuum we had in there was awesome. So then you would have a MOT, an optical trap. You would have 3 intersecting beams that would produce a lower potential for these atoms to be there. So these are your bosons, right? So you make a boson condensation by cooling them down and everything. So what about your fermions? Your fermions are lithium-7. So it's actually lucky that in the lithium system you have two non-radioactive atoms, that one is a boson and one is a fermion. So you cool those down differently. Use a laser slowed beam. By putting them into the same system, you squeeze them down, you put them in together, and then you allow the boson condensate to cool down the lithium-7 atom, then you get voila, your Fermi degenerate gas. So this is what the schematics looks like. This is what the sucker looks like. So, and here's Waldo. So it was really exciting, really complicated, and really tiring. So here, and here we go. So, sorry, the other way. Okay. So here you have the lithium-6 source, heated, so it produces hot lithium ion. You bring it into this main vacuum system. You have the lithium-7 oven over here. You cool it down from this direction. You need to have Helmholtz coils to cancel gravity. You need to have these high current lines coming in to be able to do the switching of the potential you need, and so on and so forth. So this was actually the biggest project I worked on, in the sense that not everything was mine. I couldn't make everything. So there were 2 or 3 other grad students and a postdoc who was also working on this. So it was a learning experience. And it was a lot of hours. And the question of, is this what I want to do for the rest of my life? So when I entered physics, I didn't really know what it was. I mean, I know that sounds terrible, but do you really know what an atomic physicist does? I didn't when I entered. I knew that I was good in math. I knew that I was good in physics. My parents had me have an engineering major when I first entered grad school. So for a year I was an engineering major, and then I threw the gauntlet down and became a physics major. So when I went to my atomic physics group in grad school, I didn't know what atomic physicists do, and I got lucky in that what they did was exactly what I wanted. You know, the quantum mechanical work and positron traps. So this is a more molecular and optical part of AMO, and it wasn't as exciting for me. So the question was, this is what I want to do for the rest of my life. And I think my advisor at the time was rather upset that I had an invite to go to a really good university for a technical back position, and I just couldn't see it. And it was extremely scary. It was extremely scary because all I know is academia. All I know is professors. All I know is what they do. And so I kind of sent out the feelers to all my professors and said, I want to do something different. Do you have a contact? Is there anything you can help me with? And I think they were disappointed, but they were like, okay. So they actually told me several labs that I needed to go to. So this was a leap of faith, but I want you to know that if you have the right degree, I mean, you can make those leaps of faith. You know, it's different having a PhD in physics than having a, oh, I'm going to put my foot in my mouth, than having a PhD in history, right? I mean, let's be honest, right? Sorry. No one take this, please. Okay. So just know, having a degree in physics is good. Okay. So I didn't know anything about research labs, but to be honest with you, I knew that I needed to go somewhere that was large enough that would allow me to learn, right? I mean, I know antimatter, and I know boson condensate. You know, what company is going to do anything with that stuff? So I asked my professors, and I found big labs, GE, what's the other one? Whatever, GM, sorry, Sherman Motors, of course, Ford, whatever. So I knew that I wanted to go to a large diverse research laboratory that would allow me to learn what I needed to. It's kind of very interesting. When I was doing my positron work, I knew that I was the world expert, maybe one of 2 or 3. But I was the world expert in the positron work that I was doing, and 5 people in the world cared about what I did. The rest of them were like, whatever. So it's kind of nice to work in something that when you actually see someone who's a stranger and talk to them and you say what you do, their eyes don't glaze over. Right? Like, what the hell are you talking about? So, and work-life balance. I mean, It's more than I thought, it's more work than I thought, but I have a feeling that I work fewer hours than you do, so just a guess. So, but working in industry is very different, so it's the dichotomy of a mature field. You know, people ask me, my mom asks me, do you do physics? And I'm like, okay, so what's the definition of doing physics? What I do are things that are not in physics textbooks, so to speak. Some of them are, but are not, because they're mature fields, right? You know, ultrasound, infrared, you know, some of those things have been done for many years. The problem is the way physicists do it. So here's my joke. The milk production at a dairy farm was low, so the farmer goes to a physicist at a local university. After thinking hard for 10 minutes, the physicist has an aha moment. He turns to the farmer and he says, consider a spherical cow with a simple harmonic motion. So we don't have any spherical cows in industry, trust me. So in a way, it seems like I have to relearn things, you know. I cannot make my experiment not have to worry about nuclear physics by making a positronium, right? I mean, positronium, you don't have to worry about QSD, you don't have to worry about all of those nuclear strong forces. I cannot do that as industry. So what I've done is material characterization, non-destructive testing, alloy designs I tell you a little bit about, and some things that are more close to manufacturing. How much time do I have? Am I doing okay? Yeah. Sounds good, no problem. Okay, so you know what I did in grad school, right? And it's awesome to say I work with antimatter. In fact, I love it. I had someone come up to me and says, oh, you're a physicist. I hear there is such a thing as antimatter. Yes, attractive. So that part of it is very cool, but, okay. So at Ford Motor Company, we care about cars. Now, I'm not gonna do a good job of trying to express this to you, but I do want you to think about this. The lines at Ford Motor Company and other companies like General Motors and Chrysler, when the production is good, you have a car rolling off the line every minute, okay? So like in the last 20 minutes or whatever that I've been speaking, 20 cars have come through in here. So think of that cadence, right? Think of the fact that every time something goes wrong with something on the line, and I went to the Mustang plant and it was amazing. So at one end, they started with metal sheets, literally sheets of steel and aluminum come in. And at the other end of it, the car rolls out. And I'm still amazed that more times than not, they put the key in the ignition, they turn it on, and the darn thing turns on and, you know, like drives away. It is a complete, and it's a complex thing. It is, you know, the days of having your father or mother being able to tinkle with your car are kind of sort of gone, and it's really, really complicated. It's really amazing. So we're putting more and more into the cars because fuel economy is an issue, right? So I hope all of you believe in climate change. If you don't, let's talk about that. So as much as I think sometimes the government goes overboard with some of the regulations that they have, we are definitely interested, and General Motors is, and Chrysler is, and Toyota is, in being able to introduce lighter vehicles such that has more fuel economy. So in the case of aluminum engine blocks and cylinder blocks, which most of the cars have it right now, so it used to be steel, now it's aluminum. So imagine that you need to make a softer metal that has lower strength, be able to handle the ignition, and not only that, the combustion, but also we're trying to run everything hotter because it's more efficient and it gives you better fuel economy and so on and so forth. So we want to improve how long it takes for a new engine design to make it to the market. We want to improve quality, and we want to reduce cost. So all of those sound like the kind of boring things that someone at a company would say, but I want you to know that there are really good people, and I'm not very good at designing things for industry yet, I'm learning, but there are people that see vice presidents say things like this and come up with experiments in simulating cast aluminum components. So what we want to do is a portion of, or I should say is probably a superset of CAE, computer-aided engineering, okay? You want to start before any money has been spent making a die, casting an aluminum, any experimentation. You want to start with the computer initial geometry of your vehicle. See how it fills with liquid metal, okay? How all the crevices and all of the complicated shapes get filled out. You want to thermally treat it because that actually increases the strength of the alloy. You want to know what the microstructure is. That's supposed to be a micro, sorry. Supposed to be a microstructure. And then from that, you can figure out the defects. You know, what is the porosity that you have in there? How ductile is it? What is the fatigue strength, you know? Because these things in your car need to last a long time, and they will, undergo a lot of stress in that case. Okay, so to be able to do that, believe it or not, you need quantum mechanics, okay? So when you look at almost any material, they're not the simple ones we think of. Again, you know, if you ask a physicist, what do you think of an aluminum, they think of an FCC structure and everything's beautiful and there's nothing wrong. In reality, what makes your alloys and everything else stronger are the strengthening particles that you put in it. So just an example, in aluminum copper alloys, it happens to be these disc-like materials that are harder, that put the whole thing together. So think of it this way. I have a big vat of molten aluminum, and I put a whole bunch of other stuff in it. I put in a little bit of copper, a little bit of manganese, a little bit of magnesium, and then the whole thing is molten, the whole thing is mixed together. I pour it in this really complicated casting, I heat treat it, and voila. These beautiful disc-like things happen, they kind of grow, and they provide the strength that I need, okay? In magnesium alloys, they actually are little plates. They look like this. So again, you have this molten material is all mixed up together, and you heat treat it, and these beautiful precipitates form, right? Which is really awesome. And they form in a very specific way. Like they don't just grow in, weird, they have specific angles and such. So you can use TM to look at them. You can see what they look like. So this is magnesium on the outside, and there is a structure on the inside. You can see what the walls are. It's awesome. It's really, really cool. So what we want to do is ask the question of, how can I introduce more of these, right? How can I put more of them in the alloy? How can I make it stronger? And how can I do it such that it doesn't cost me a lot of money, right? If you come up with a really complicated process that raises the price of your engine by a factor of 2, no one is going to go after it because you're not going to buy that car, right? So that's the issue that you have to deal with again, the dichotomy of the mature field. So believe it or not, I use atomistic simulations to be able to understand how these things grow. So what we literally do is, in a way, start at the quantum level, okay? So let me tell you through these precipitates. One of the things that tells you how big they grow and in what shape and direction they grow is the interfacial energy between the matrix and the precipitate. So just imagine you have this other material trying to grow in this matrix of aluminum or magnesium, but there's of course that interfacial energy at the surface that wants to be minimized as much as possible, and there's also strain fields and everything else. So what we do in this case, what I do in this case is I know from X-ray work what the crystal structure of the precipitate is. I know what this material on the inside is. And what I do is I use actually commercial programs to just make a little cell, a supercell, that has this interface between the magnesium down here and the precipitate in the middle. I then use density functional theory to run it through the system, and it will lower the energy as much as possible. It tells you where the lowest energy is, which tells you what the energy of this interface is. And then we put that information along with the energy from the strain into the system that tells you how quickly and at what temperature these things grow. And then that information goes into another program that carries it from the nanometer scale to the micrometer scale. And then that goes into another program that takes it from micro to the millimeter, which it tells you how strong the material is and how ductile it is and so on and so forth. But at the end of it, and I am the only person at my lab who does this when I get the chance to do it. So you become the one person that does that one thing that perhaps none of your colleagues want to do. And that's a good thing, right? I mean, that's what they say, you want to be. And I gotta tell you, when they first told me that I'm gonna do quantum mechanical work on this alloy, I thought they were insane. Because I thought I would have to go back to grad school. It somehow never occurred to me that there would be all of these physicists talking to material scientists and making commercial programs. I mean, these programs, you can't just use them, nilly-willy, but you literally can, pay a license, learn for a week or a month, and then build your own alloy and have it actually give you data and information that makes sense. So that's actually really, really exciting. So that is as close to physics as I get. So when my mom asks me, do you do physics? I'm like, oh yeah, I do physics. This one isn't quite. So I was looking for a picture to make you excited, and this is the best one that I could come up with. Get excited, okay. This is the welding, the robotics welding line at Ford Motor Company for one of the cars that's coming down. So all of these yellow things are big robots that do welding. So in this case, they do resistance spot welding. So pretty much two electrodes come together, zap, and you melt the material and you put it together. And I gotta tell you, I find this cool. It could be 15 years in industry that I find it cool, but I find it cool. So you have a situation like this. Again, you look at this and you go, as a physicist, what the heck am I gonna do with that, right? I mean, how do I have anything to say about this where I'm not an engineer, I'm not a mechanical engineer, I don't know how to run these welding machines? Well, the process itself cannot be simpler, right? I mean, this is just right out of one of my papers. You put two sheets together, you put two electrodes on either side, run current through it, you melt the material in between, you join the sheets together, voila. What could be easier, right? The problem is that we're introducing new alloys. So remember, all of the lightweighting we're doing, we're replacing all the steels with either high-strength steel or with aluminum. And aluminum is very different metallurgy. I was chagrined that there was more than one person at my bigger organization that they're like, a metal is a metal. I'm like, okay. It's also good to be smart enough to say, no. Steel is very different from aluminum. But I have my first grad student, and I am ecstatic that we can talk about this stuff. We can take this and find the right customer. Sorry for using that word. You have to find the right customer to be able to want you to do the work. And the work is that she has these resistance spot welds made. She cross-sections them, she does the metallurgy on them. You can clearly see the fuse zone that you have around them. And then she does hardness testing. So this is a beautiful grid of hardness testing that it does, and it clearly shows that one, these sheets are not uniform by far. They have a softer middle, which was fascinating to us. And then on top of that, you make the nugget, and the nugget is softer. So the question comes in, you have the soft nugget surrounded by this thermomechanically affected zone that's harder. How is it gonna fail? How are you gonna be able to pull a button or not pull a button? Ultimately, and I'm never gonna be in a situation like this, but you go to a court and the judge says, someone is telling me that you put the wrong welds on the car. Prove to me that you did as good of a job as you could possibly do. And this is the kind of information that ultimately I need to give to the welding engineer that carries forward. So there is a lot of really good work that you can do in industry. So do not think that what you see in grad school is the coolest thing that you're ever gonna see. It might be one of the coolest things, but it's not the only coolest thing that you see. So keep your horizons open. Okay, so lessons. A physics degree is valuable. It teaches you how to learn. It teaches you how to study. You have a rigorous background. So when I interned for Ford Motor Company, I was in the physics department. Within a couple of years, they dissolved that. I was in the physical and environmental sciences department. Then a few years after that, they dissolved that. I was in the materials and nanotechnology department. That's when nano was everywhere, right? You put it in every word that you could. But then I got cold, so we're like, we can't have nano there. So then I became part of the materials and processes department. So I went through it all. It wasn't fun, especially when the economy went bad and they were getting rid of people and everything else. But believe it or not, I felt like my physics degree and my difference and nerdiness were part of the reason that maybe I made it through. So you can change paths, exactly what Christine said. You can change paths and be successful and happy, but you need to have the right background to do it. Again, I apologize, but a PhD in history might not give you the same flexibility as a PhD in physics. And a PhD in engineering will give you lots more. I'm not saying, I'm not just saying physics is the high end of it all, but it is a really good background to have. Being different is good, right? My colleagues come to me and I ask them a lot of stupid questions that they know, but I have a different perspective on how to do some of the analysis. But being different can be bad, right? So when you go in grad school, be aware that ultimately you might need to talk to someone who cares about materials and not just baryons and mesons and positrons and positronium, right? So, I didn't know what a yield stress was. I didn't tell anyone, I didn't ask anyone. I went to, Wiki and, then worked my way to some kind of book. But just keep in mind, you want to be diverse, but again, a degree in physics is very good. Remember the world changes, funding sources changes. I wanted to do precision measurements in quantum mechanics when I was in grad school. And by the time I left grad school, there was pretty much no way I could do that except for work many hours a week or so, and I wasn't ready to do that. Problems get solved. So one of these days, my boss is going to come to me and say, you know what, I think we have beaten that down enough. Move on to something else. I have to go something else. But the most important thing is you change, right? I mean, this Bita is really, really different from the one who went to grad school. I would have never thought I would work at Ford Motor Company. In fact, when I was thinking about taking the job, I was thinking to myself, oh my God, when I drive, I'm gonna see all Ford emblems everywhere. What if I hate my job, right? It will be a continuous reminder of how, sucky everything is. So, it's all good. So a physics degree is valuable. You can have really amazing experiences out there. So go and get them. Thank you.
A little bit over time, but I think we have, if you guys are okay with saying, maybe a couple of questions, 2 questions. Do you have questions? Yes.
Sure. When you're working in industry, do you get a chance to publish like academic papers?
Yes, yes. So it depends. Sometimes it has to be delayed. So one of the projects that I worked on, we couldn't publish for a couple of years to do that. But most of the time, it is not really a problem. It also depends on where along the chain of product you are, right? So I am way at the long-term end of things. So most of the time, what I say is academic enough that it doesn't really connect. But I do know I have colleagues that they were not happy about the fact that there were grad students we had who couldn't publish until. So you got to be careful. And the closer you get to product, the more you can have problems in that case.
Ready for one more question?
How big was the learning curve when you were transitioning into your industry field?
So, yeah, because, so confession. I don't mix with condensed matter very much. Sorry, when I got done with my last course in condensed matter, I was like, So, and materials is all condensed matter. So, it was huge, but I think I also made it more difficult than it was because coming from a physics background, so let me tell you this, if you get a PhD in physics from the right institution, and I say that because I don't believe that every PhD is smart. There are some really dumb ones out there. So, but I've noticed that we have a different standard. The way we write papers, the way we write reports, the way we do things, we just have that extra little bit of, let me read it a second time, let me read it a third time to do that. So to a certain extent, you end up having that extra level of expectation that then helps you in going that extra step, so that when you learn something and you come back, it ends up being something of value to the person. I personally would have loved it if I had taken a material science course when I was in grad school. it would have never occurred to me in a million years. So I recommend to all of you that you're gonna be in grad school, if you go to grad school for a long number of years, okay? Taking one course or two courses, even if your advisor is gonna look at you and go, really, you're wasting your time taking material science, it's worth it. It is really worth it. I wish I had done that such that the slope wasn't as steep as, it turned out to be. But it turned out to be okay. Like, I didn't cry every night. I didn't even cry every week, so,